Hey folks, so in this video I want to do one more example of using recursion with Fantastic Four. Now for this one I'm going to try to do something that's a little bit more complicated and also an example of a situation where the recursion is kind of very naturally used. So the problem I'm going to be solving here is printing a list. So I have this, right? I have some data structure which is a list which has these nodes in it, and all the nodes are the same, right? They're the same class. There may be something called like a linear node or something, and they're all kind of connected in a certain way. And what I'd like to do is I'd like to print out the contents. So let's say I have A, B, C here. So I would like to print out to the screen, A, B, C. So let's try doing this with recursion. All right, so number one here, formulate the size n problem. What is the whole size problem in this situation? The whole size problem is to print out the entire list. So basically, right, I can imagine I have this one function called display list, and it takes in a head node, if you would, right? It's really called node here, but somehow, right, the idea is, right, normally for a list you have something that's like a head. So it's like, well, you're starting over here, and then it's like, well, your head right ends up being kind of this thing that would be passed in. So it's like, I'm going to start at the head of the list and display the entire thing. Okay, so that's our full-size problem. Then what about our stopping condition and return value? What should we have there? Well, we kind of have two choices. We could either look at we could say that our stopping condition is being asked to display an empty list or a list with one element. Here we're basically going to go for the empty case because that's the most trivial one. If I have an empty case, there's no work to do. So if I am looking at a list, asked to print it, and I see just an empty node, just return, do nothing. All right, number three, formulate the size n problem, right? So what is the subproblem we're trying to do? Well, the subproblem is basically going to be to display the tail of it, right? So this is basically the whole list here, just point out by head. But then we also have this idea of, a list basically looks like, some leading node, right? This thing over here plus a tail, right? So this thing over here is called a tail. Sometimes people will even write something like this. It'll be like list is equal to a head followed by a tail. That's sometimes what people will write. Because it's like, well, I'm looking at one node and I know that node has a .next variable, and so that leads me to somewhere else, right? A bunch of other nodes, basically the tail of the list. So if I want to print out the subproblem, right, basically what we're saying is, oh, hey, the little bit of work I can do, right, is basically say, hey, I'm going to print out this, right, to print out the first element, and then recursively print out the rest of the list, the tail of the list. So that's what we'll put here. We'll basically say that our recursive case, right, or our subproblem is to display the list, that basically is starting, after the current one, right? So no .next, right? So it's like, well, initially we're looking ahead. If we do if we're doing .get next, it's like we're going to look at everything that's after it. All right, so we're displaying kind of the rest of the list. So yeah, in our diagram, basically, the part one, right, is displaying this part versus part two is displaying this part over here, right? So the whole thing versus just the tail. All right, so how do I construct, the whole problem from the subproblem? Basically, I want to do a little bit of work, right? Act on the node and then have the code from the subproblem. So over here, right, display the current node and then recursively call myself, on the tail of it, right? And that should give me my nice recursion action going on there. All right, so I have the complete code here. This, right, is it's not too complicated. Basically, I have my two versions here. So I have an iterative approach, and then I also have my recursive approach. And what maybe we can see a little bit here is basically that the recursive one is a little bit simpler. So I guess I can talk through these really quick. So look at the iterative one, right? So this is saying I want to create a way to review the concept of a list without using recursion. What happens is I have to do something like this, where it's like, well, I'm going to create an iterator variable. And this iterator variable, I'm going to have a while loop that basically checks it against null, and then I'll print inside, and then I'll move that iterator forward. I'll go iterator equal iterator.getNext. So it's like, if I have a list that looks like this, effectively what I'm having to do, right, is manually move a little arrow along it. So it's like, well, I have an arrow that points down here, right? These are kind of the backbone changes that I'm drawing in right now. But I could have an arrow, right, that starts there, then needs to go there, and needs to go there. That's my iter, right? That's a very typical way to navigate a list. But if I do this in terms of recursion, all things end up being a little bit simpler. I just completely lose that variable. So I don't have to worry about this at all, right? That disappears. Iter disappears over here as well. I just check to see, oh, hey, is it not null? If it's not null, display it and recurse, right? Otherwise, nothing happens. So it's a little bit simpler. Now in another video, which will be optional, I'll give you guys kind of more of a walkthrough about how to actually write this code. All right, so that's all I got. So this is kind of an example where I have a little bit more natural place to use recursion because lists, right, we talked about our recursive data structures. So kind of it's usually natural for us to use a recursive algorithm to go and explore them, to go do work on them.